All right, let's get started. Welcome everyone to today's University of Texas Energy Symposium. I'm Gary King, Assistant Director and Research Scientist at the Energy Institute here at the University of Texas at Austin. And today it's a pleasure to have Dan Dalton. But before I introduce him more formally, I will go over the talks that are upcoming. Next week, we'll have a talk from the lead scientist at the Nature Conservancy, Joseph Kiesecker. If the road to renewable energy transition must pass through crowded land, so we'll learn about land conflicts with energy infrastructure. And then November 5th, so election day, the state of energy in Mexico. Ariel Ramos is the Vice President of Global Partnerships for a law firm, and Houston represents clients in Mexico. And he has a specialty of focusing on Mexico. Today, it is a pleasure to invite Dan Dalton, Vice President, Global Partnerships for Wisk Aero. He's also volunteer chairman of the Texas Advanced Air Mobility Advisory Committee, and so we might learn a little bit more about that. A little bit of a biography of Dan. He works with regulators, policymakers, and industry partners. He's a key contributor to Wisk's strategic efforts to bring our self-flying air taxi to the sky. So this is about flying cars. Prior to joining Wisk, he served as Executive Vice President of Strategic Partnerships for Airspace Systems Incorporated and a visiting scientist at Lawrence Livermore National Lab. He's also had engineering and leadership roles at General Atomics Aeronautical Systems and the U.S. Department of Energy. He's a commercially rated pilot, which maybe is a necessity to have this role, perhaps, and has a passion for the aerospace industry, enjoys flying drones, land and sea planes, and teaching the next generation the wonders of flight. So it fits the bill for this role. So he's going to provide a deep dive on the new age of electric aviation, including advanced air mobility, or AAM, the electric vertical takeoff and landing, or eVTOL, aircraft proposed to transform aviation, promising sustainable and accessible air travel for everyday commuters. So he's going to tell us about Wisk Aero's self-flying first approach to autonomous air taxi by electric air vehicles. So with that said, let's welcome our speaker today, Dan Dalton.
Thank you, Carrie. All right. So you know everything about me. So basically, yeah, I'm a recovering engineer. You'll hear that a lot. I made my way into business. I grew up at the end of a runway, which is basically how I found this affliction called aviation. And so we'll talk not much about me, luckily for you, but we'll talk a lot about this aircraft and the future of aviation as it relates to sustainability as well as automation. Sorry. With that, we'll start off with this video, who some of you may have actually seen this video before, but we'll play this, give you an overview of what we're actually doing at Wisk. The photo of Jay's kid, because that will be the person that we're actually trying to use the most in terms of rideshare. So awesome. All right, so a little bit about Wisk. So we are about 800 folks strong now in 5 countries around the world. Most of them are the folks that are with the company are in technical disciplines. Some of them, like I said, are recovering engineers like myself who found a way into business, but really strong in the engineering, certification, manufacturing, and then flight tests disciplines. Like I said, 5 countries around the world, really looking at different strengths and capabilities in those different countries. So for example, Canada, really great set of individuals around avionics and the development of flight control systems and that type of thing. Australia is fantastic for an actual early entry into service, maybe. So a lot of different capabilities that we tap into around the world. Relative to our competitors, a significantly greater number of patents and flight tests. With some of our competitors, this is actually an order of magnitude more patents than they have. So we've been doing this for a long time. And of course, one of the key differentiators for our company is the Boeing company. Last year, we became a wholly owned subsidiary of the Boeing company, which allows us to not only tap into, it's now public, it was not public last year, but it is now, that of those 800, about 100 to 150 of those are actually Boeing engineers and certification experts and technicians embedded in the Wisk program. So, not only are we able to tap into Boeing's great technical expertise, but also their global reach, speaking with other regulators, global supply chain, great amounts of capability. That's a huge differentiator for Wisk among our competitors in the industry. And so, but we've been doing this for a while. So the company first started in 2010. When Larry Page and a couple of others got together and said, Larry Page of Google, you probably know the name, got together and said, could we actually create an electric vertical takeoff and landing aircraft? So within about 12 months, they made that first aircraft there on the left. It's the Gen 1. And that is a prototype, a scaled prototype, a little bit bigger than maybe two of these tables pressed together. And that was just to show that you could actually use a battery to take off, to have an aircraft take off vertically. So very quickly after that, they said, okay, that's great. We could do it for a few minutes, maybe a few seconds of flying this aircraft off the ground. Let's put a human in it. So they then took that design, scaled it, still made it electric, and they made it actually a conventional takeoff and landing. So it takes off on wing-borne flight. And that's the Gen 2 there that you see on the slide. That one flew around with a pilot on board, did great things. And then, of course, classic Silicon Valley, they said, okay, that was great. Now let's put them all together and do it again. So in that same year, they then built the third generation of the aircraft, which is the ability to take off vertically with electric battery and have a pilot on board, fly horizontally, and then land again vertically. So we believe this is actually the first time in human history that an electric aircraft with a fly-by-wire system took off and performed a transition from vertical to horizontal back to vertical. That aircraft was nominated for a Collier Award in Aviation Excellence, but lost that year to a small company called SpaceX. So next year, so then we fast forward to the Generation 4 aircraft. And that's the first time we took the pilots out. And since Gen 4, we have not put a pilot back in our aircraft. The real vision for this, which we'll talk more about, is if you have a human in the loop that's on board the aircraft, you are automatically capping yourself on the total scale that you could actually see yourself tap into as it relates to getting into the industry. And so humans slowly become that limiter on the ability for the company to grow. So with that, and we'll talk about the safety side too. So with that, we took out the human in around 2017 and haven't put the pilot back on board. But we did kind of change the airframe a little bit. You can see we went from a high wing to a low wing. We changed the propulsion systems a bit, but always using the foundation of the aircraft systems, propulsion system, battery system, and control system. Between 4 and 5, Gens 4 and 5, they look pretty similar, but they're actually quite different under the hood. A lot of advancements in the avionics and whatnot that really helped us drive kind of into this next generation, which is the Gen 6 aircraft. I know, creative name. But we'll talk about more about that in a second. But we believe that this is the type of experience and knowledge and skill sets that you need to have to truly bring this electric form of aviation that is autonomous safely into the marketplace. So let's talk about safety. Aviation heralds itself and prides itself on a high level of safety. You look at the number of car accidents, the number of people who die in car accidents every year, other forms of transportation. Aviation holds itself to a very high level. And so for that, we believe that the first way to introduce an autonomous aircraft is to embrace that high level of safety. And so in that regard, really trying to drive to the commercial levels of safety that you see today in traditional kind of commercial aviation. That being said, while we have an autonomous aircraft, we will always have human oversight of every single flight that is flown. We want to make sure that we're simplifying this design. Sometimes safety aspects, safety challenges can creep in when you make a design overly complicated. So how do we make it as simplified as possible, but at the same time, also make sure there's no single point of failure. So when you hold these different tensions in place, you can actually design a really amazing aircraft and service for people in the future. So let's talk about the aircraft first. This is fun. So, one of the key things that we had to do was, as I said, we're kind of reimagine how people think of aviation. Traditionally people think of, okay, there's kind of 2 sets of rows of chairs, and you got to get in there, you got to throw your bag overhead, and it's a pain in the rear end and all that kind of stuff. So we started with this kind of thing, we call it the Woodbird. So we started with this box effectively. And you start seeing, okay, where do you want to have people sitting? Do you want to have them facing each other? Do they want to be facing away from each other? How does that look? And so you start going through the iteration process of, okay, where would they put their luggage? How would they get in the aircraft? Once they get in the aircraft, what do those doors start to look like? How do we make sure that this is accessible for everyone, as many people as we can, whether it's physical impairments, visual or auditory? All of these different things start folding into the design process. At which point you then emerge with your first design, which is that top right corner, which then you know from there, now all the other design changes start to really begin. So this is kind of what the interior looks like from a passenger perspective. The key thing, if you're an aviator, you'll notice that front left corner, there's some pieces missing, largely these stick and rudder pedals. But otherwise, it's designed to really have that automotive feel, because we're actually taking the automotive mobility rideshare concept and putting it in the air. So we wanted to make that as natural as possible for folks. And so that's not just in the physical domain, but also in the digital or the information space. So, as we all know, when we ride in a rideshare, we're all looking at the black line or the purple line, depending on your service. And we're always wondering, where's that line going? And is the driver on that line? So we had to take a lot of those learnings and customer surveys and feed that into our own system. So that headrest display that you saw on this previous slide, that is the passenger's information system. There will also be an app if you want, but that's really where most of this comes in. And so as you can imagine, when you're flying along, we all know how cars operate. There's a left-hand turn, there's a right-hand turn, there's a stop sign. We can anticipate that type of stuff. But as we move people into the air for the similar type of mobility, we have to think about what is it we want to show people cognitively. So for example, you don't know that necessarily the plane's going to make a left turn, or that it's going to descend, or that it's going to make a right turn, especially if you're in the clouds. So how do you convey that visually to people, or auditorily if they can't see, in a way that people are not concerned about what the aircraft is doing? Suddenly there's a bump, and so do you think, oh my gosh, the plane's flying out of the sky? Or is it just that there's a little turbulence? How do you convey all that to the passenger? So as an example, this top row is about, do we let people know 3 seconds ahead of time that they're going to be making a turn? Do we let them know 5 seconds, or is it 10 seconds? How do you find that right amount of time that makes people feel comfortable that they know what's about to happen? No one likes to be surprised, especially in airplanes. At the same time, the bottom row is about how we convey the traditional safety information. So you put your seatbelt on, this is the emergency exit, but then using the power of the information we have available, we can do that in sign language. We can do that without visuals. We can brighten the screen, make the icons bigger. We can do it in different languages, all again trying to tap into as many folks to be able to ride on these aircraft as possible. So this is the Gen 6 aircraft. As I mentioned, it is autonomous. So it does, again, if you think about traditional aviation, there's a lot of monikers in aviation. So one of them is aviate, navigate, and communicate. Those are the 3 things you should do as a pilot, or in this case, the aircraft should do, to be able to ensure safety of the aircraft, its passengers, and the airspace. So we will always have a human looking over the aircraft, and we'll talk more about that. As I mentioned, the safety targets are around kind of the same that you would see for safety critical systems on a large jet, for example. We're going to carry 4 folks, and the aircraft is about 50 feet in wingspan. That's designed to fit into existing helipads and heliports and airports and stuff like that. Our range is 90 miles and the speed's about 100 knots. So that really, the reason for that is around our business model. We're trying to move folks kind of around a city or from the city center out to kind of suburban areas. We're not trying to take them from Houston to Dallas. We're trying to take them from the Domain to Bergstrom in 10 minutes on a Friday at 5 p.m. So how do you get people moving around in that way versus moving them, large distances? Plenty of folks in the industry, our friends in the industry, are going after that kind of Houston to Dallas, or maybe even LA to Dallas, that kind of thing. But for us, we think the business model that is for this design of this aircraft, the right one is kind of moving folks around. Again, okay, so Friday or Sunday evening, you go from San Antonio to Bergstrom in about 20, 25 minutes. So would you folks take that service? One person, good. So the key number on this entire slide, I would argue, is the charge time. So that is the thing. This airplane does not make money on the ground. So every minute that's on the ground is more time that's consuming money versus generating revenue. And so every minute, every second that we can actually take off of that charge time is the ability for us to provide the service to a greater number of people, more operations, all that kind of stuff. So that's probably one of the most proprietary numbers. I can tell you right now, that's not 15 minutes. It's not really 15 minutes, but that's the number we're happy sharing with folks. That number is a very proprietary number, and everyone's trying to get it down just even a few seconds off. And that's largely limited by the technology of our time, honestly, lithium-ion batteries. How we can advance our understanding of lithium-ion batteries or solid-state batteries as we go forward, that will significantly change and, again, open up this capability in so many ways. Carry on with the personal stuff. So this aircraft has a useful load, which is like the load that you can actually use. Well, it's named. It is about 900 pounds, and that's for people and for cargo. Mostly they're carry-on bags. We're not looking to move a family of 7 to have them go have a great time in Switzerland for a week. That's not what we're doing. We're trying to move folks just around the city. But the nice thing is, in a traditional aircraft, normally your useful load is divided between your luggage or cargo, your people, and your fuel. But because we have an electric aircraft, we can actually take the fuel amount away and give it to people and to bags. So the key parts of this aircraft are obviously on the electric side, you've got not only the spinny parts, but also the actual electron holding parts. So electric motors and storage are really, really critical. We personally at Wisk have decided to vertically integrate that, which means we're actually doing our motor development, we're doing our own battery development, because we believe that that is the area where you're going to need to build out something, iterate on the design, build it out again, keep doing that. So we want to make sure that we are in control of that versus a third party who you say, oh, okay, well, this didn't work. You send it back to them. 2 weeks later, they say, okay, we looked at it, and they send it back to you 3 weeks later. We're trying to do this as quickly as possible, as safely as possible. And so we believe vertical integration for our company is the right way to do that. Then you've got other key elements, especially around the autonomy side, which are around the avionics, the communication systems, and then, of course, detecting and avoiding things, especially in the air, which we'll talk a bit about. So on the battery side, on the power side, the batteries are extremely unique in these aircraft. And it's not just ours, luckily. It's a lot of everyone who's doing the eVTOL part of this. And the reason is because the vertical part of this component, so this aircraft, many of us are, sub 10,000 pounds. But many of us are also greater than 5,000 pounds. So that's a pretty weighty aircraft, especially when you have people and stuff on board. So you need a battery that has the performance, we talk about like, 0 to 60 in X seconds, right? You need to be able to do that for a couple of minutes. And you need to be able to hold that aircraft, not only break ground or leave the earth, but be able to safely fly up for a couple of minutes and then transition to horizontal flight. So that vertical component actually requires a huge demand, a huge power demand on the battery systems. Then once you get into wing-borne flight and you're flying on the wing, you actually can reduce a lot of the load on the batteries. But that means that the battery needs to be able to go into a high endurance phase. And so that's where you start looking at like car batteries, right? 200, 300, 400, 500 miles in the future, right? How do we make sure to extend the battery life of that vehicle to be able to give out those electrons every once in a while? And then you get back down to landing and you get back into that high power mode. So what happens is you have to have a battery because you can't have different types of batteries that do different things on your airplane. You want to have one battery. So you have to have a battery that has that high power density, that long energy density, and then that high power density again. So it's a pretty unique capability. And then you have to be able to certify all of that through the FAA or other regulators around the world. And that all of that type of mentality also goes into the power system. So how do you build these, for example, 12 motors that we have with those battery requirements and the battery technologies that exist today and are certifiable today, but also be able to do that in a high level of safety that you could actually lose a number of these motors, whether it's a bird strike or blade out or some other thing happens, and you can still make a safe landing. So it's a key part of this. And so what we do is we test the heck out of this thing. So this is an example. This is our little like mobile wind tunnel. We actually, that blue thing can blow a significant amount of air out. And so we can actually test how the various test stands even respond, let alone the actual aircraft itself. And so another thing we do is called our Iron Bird, which is where you start taking, before you actually build the fuselage itself, you start taking the key components and putting them together, wiring them together, seeing how they interact on the ground. Hence, it's an Iron Bird. So See if this thing will play. There it goes. It's super catchy. So you can see how with that design, you can actually see how, let's take loads, for example, let's take electrical loads. So you can see how even with just 4 motors, if you try and overspin one or underspin one, how does that affect your load and your load balancing across the electrical system, especially as it relates to the batteries. Do you have thermal runaway, any types of issues there on the battery cells themselves? You can look at mechanical loads, you can put strain gauges and those types of things on there to see kind of what's happening as it relates to actuation and these other things. So that Iron Bird fits in a cage roughly the size of this room. And there's all sorts of exciting safety things you have to do because at any moment it could do its own thing. So, but yeah, that's kind of in a large industrial facility in California. So then once we started to integrate those kind of mechanical and electrical systems, there's also the autonomy side of this. And so what are the ways that while we're building out the hardware and the software, frankly, what are some of the other subsystems that we can actually test and try out in the real world after we've simulated them? We spend a lot of time in the simulated environment. So we'll talk a little bit about radar, for example. So detect and avoid, one of the best ways that we've found is to use radar, LiDAR and acoustic and visual. There's all sorts of different ways, forms of physics you can detect something coming at your airplane. Radar for us works really well. So you put that radar system, you model it out in a simulated environment, then you have a real world simulator, right? And then like you test it out to see what types of encounters can and cannot be affected by the radar, how it does in that. Then you take that radar out of the simulated world and you put it in the real world. But you don't want to wait for your Gen 6 airplane, so you put it on a Bell 206. So that's a great example of how we use surrogate aircraft to be able to test out and to truly reduce the risk associated with the development of our program. So this is the 206. We put a lot of holes in this helicopter, but the good thing is you can hot swap racks in the back, like in the bottom right corner. You can put humans in there, and a lot of times it's kind of funny. One of our test engineers refers to himself as a meat servo because he's basically doing what he's told by the computer. So he is the meat servo. He pulls all the levers and does all the things to make the helicopter do what it needs to do. Back on the ground, you've got multi-vehicle supervisors. So one of the key things for us is that not only will we have one human overseeing an aircraft, we'll have one human overseeing multiple aircraft. That way, again, the operations can scale, more people can use the service, all that good stuff. So this is what our fleet operations center looks like. It looks kind of like an air traffic control center. And so these folks are all, the folks in the front, kind of in the front of the, well, in the back of the image, but in the front of the big screen. Those folks are all managing individual aircraft and then their supervisors sitting behind them. Another thing that we have is that over in the aircraft, each seat has a call button, just like you would have on a big aircraft. And that call button actually redirects you to what we call a hospitality host, someone who's actually not affiliated with the aircraft operation. Idea being that if you do spill, you spill a shake on yourself or just ketchup everywhere or whatever else, you can ring that button and talk to someone who's not focused on flying the aircraft. Meanwhile, the multi-vehicle supervisor is just focused on making sure that the aircraft goes to where it needs to go, contingency planning, all that kind of stuff. So that way we've actually segregated the two, and it's in a very similar way to how commercial aircraft operate today. The folks up front are flying the aircraft. They are not to be distracted by things behind the big door. And so we're trying to model that too, because we believe that that's an added value of safety that autonomy brings Whereas some of our friends in the industry are going with a pilot inside the cockpit in the same environment as the passengers. So the passenger could, again, spill something on themselves, tap on the shoulder of the pilot and say, where do you keep the napkins? Then that pilot is looking over their shoulder, distracted. Then that's kind of what we believe is one of the examples of the human introduced risk or safety concern. So as it relates to autonomy, autonomy is effectively, you've got something that's helping you make decisions. It has input and then it has output, right? So the input side is the top right corner. So those are things like GPS receivers, nav, radars, all these transponders to see where other folks are and where you are. So all of these things are kind of input into the software itself, which is on that kind of top left corner, which is then taking these different signals and thinking through, okay, where is the traffic? Where is the terrain? What do I need to be thinking about if at any moment in this flight, this aircraft has a motor out, a sick passenger, whatever it is, it's thinking through those contingency operations. What happens if all of a sudden you don't have access to GPS? It could be just because you're in between a bunch of big buildings. It could also be because some state actor has decided to knock out the GPS system. So thinking through all of these contingencies is really important and key enablers to the aircraft itself. So it's fun to do R&D, but you should probably actually produce these in mass. So having a modern production system is also really important, and making sure that it's not just a kind of slapdash system, but it's actually one that's certifiable. The production system also has to be certifiable. It's also, we would like personally for Wisk, we'd like it to be sustainable, so we're not actually making the environment worse by generating these nice clean aircraft. And then, tapping into the latest and greatest in manufacturing capabilities. So for example, when you have the fuselage skin, there are lasers that shine down from the ceiling that show you where to put a part within a few mils every single time it goes into the same place. So just examples of how the production system is as complicated as the design side. So when you do all those things, it comes together and you get this nice graphic of the service that you can offer. There was a key part in that video, which I think we don't underscore enough. So to start off with, so there's no AI or machine learning aboard our aircraft. The reason for that is largely around certification. The FAA likes to see that you've got all of your software, every line of code has something to do. So as an example, at certain levels of safety, like DALA 10⁻⁹ levels of safety within aviation, you're not allowed to have comments in your software. For those of you that have ever done any sort of software coding, you cannot have a comment because that is an opportunity for an erroneous code to be compiled. So literally every single line of code has to have somewhere to go or something to do, otherwise it's out. And so in that same vein, all of the software on our aircraft is predetermined software. And that way it's just easier to certify. In the future, there might be opportunities to use AI and ML. So for example, you can imagine where this aircraft generates a ton of data on its own, just always spitting out data. So you could take that data offline and have AI go through it and say, okay, motor number 7 actually had this weird torque moment at 15 minutes and 72 seconds. We saw that again in motor number 10 over the last 2 years. Like, this is something maybe we should think about as predictive maintenance to remove those two motors sometime in the next 100 hours. So you can see where AI and ML could have a place, but we don't think it's right to have it as a navigation and aviation or an aviate, navigate, and communicate feature in the aircraft itself. So because of that, we're also doing things to focus on just flying from one point to another. So we'll have predefined routes. It's not like you'll be able to take off from Bergstrom and you're heading to the domain, you suddenly realize, oh, you wanted to go somewhere you want to go to Westlake, and you just suddenly decide to move, and then you land in someone's house. Not yet. I hope in my lifetime we will do that. But for right now, it's going to be predefined. It's going to look a lot more like a show, kind of those tram line, and we'll be able to show you those routes, and you'll decide if those work for you or not. So, but this is kind of what the user experience, the customer experience looks like. So you're sitting there on your phone, you're having some sort of squishy meal. I don't know what that is. I think it's some sort of pasta or something. And then you say, you know what, I need to go get on a plane. So you use the app, either our app or someone else's. And you arrive, you check into the vertiport. Someone tells you about what the safety briefing is going to look like. The rest of it, or at least, please don't walk under the spinny things that they're spinning. And then you get inside and you'll have their actual safety briefing. Then you will sit there, your destination, 20 minutes away or so. You get off and you go probably to your next form of multimodal. So we're really kind of a middle mile multimodal solution. So the way that our system is designed is you take a scooter, you take a city bus, maybe a ride share, you get to our launch location, we'll fly you that middle miles, and then you get off and maybe on the backside you take a taxi, you take another scooter, whatever it is. But we're kind of we're helping you bridge that overall gap. So that's kind of the service. So now more locally, one of the key things we've been really public about is our efforts to launch into Houston and the Houston area. So earlier this year, signed an agreement with Sugar Land Airport, a great little regional airport, as kind of one of the base nodes for a larger network expansion, which we then announced with the Houston Airport System later this year. So now you can kind of see where we would move folks around as it relates to, as I said, kind of in that urban core, but moving people around. And that's just the air taxi side of this. So there are a ton of other use cases. You can imagine on the government side, outside of defense, you can also imagine firefighting. So our aircraft, if it needed to, if there was a large blaze, a lot of firefighting today, aerial firefighting, they ground operations at sunset because this is extremely dangerous. So you can imagine where this aircraft could effectively become a bucket line. 24-hour operations carrying 900 pounds of water constantly. If you had about 40 aircraft doing that, you would have a significant impact on the fire overnight, which is also when the cooler temperatures are. And then when the folks are able to fly the next morning with the bigger assets, you could actually help to really mitigate the effects of that fire. Cargo, same idea. So imagine you're either flying at night or you're flying in areas where people don't like helicopters. These aircraft are inherently quieter. They have smaller motors, and it's also not a gas motor. And so you might be able to deliver into areas where you might not have been able to previously. You could also deliver cold chain in a way that previously you couldn't do with ground-based or air-based transportation. So a lot there. Medical, pretty straightforward. It's either can you transport patients back to a medical facility, or can you take a doctor out to them more rapidly? Especially for rural environments, that's a huge deal. So if you strip down this whole aircraft just to carry one doctor out to a far off place, you now extend your range and your speed capabilities away from the air taxi model. And then of course there's tourism. You can put this thing in the Grand Canyon, just fly around in circles, and you can do that safely and securely all over the place. So, a big part of this is electrification. And, over time, we do believe that there will be increased EV capabilities that will exist at airports. And of course, that reduces our carbon impact. And then we're able to kind of move into that truly electric future. I think one of the key things, I got a great question yesterday about well, how do you feel about car companies pulling back from EVs? And I said, well, it's awesome, because that if there's charging infrastructure, for example, that means there's going to be a lot of supply at a really good rate for airports to buy up a bunch of charging equipment at relatively lower cost and put those into airports, which is great. Now, the longer term, if folks who do maintenance on those charging systems decide to leave the industry over the next 5 to 10 years, yeah, that's a longer term problem for the airport. But right now, it's actually really good. So a lot of dynamics to keep in mind when you look at this industry. And so this is kind of fun. I don't think there's any catchy music, so I think you'll have to just listen to me. Last summer, Oshkosh, so it's a major aviation festival, for lack of a better term. Part of 700,000 people come to this. If you do like planes, I highly encourage you to go at least once in a while. So last year, we actually had the ability to do the first autonomous flight test at Oshkosh. So this is our team. This is a Gen 5, as you can tell, low wing. So Gen 5 took it out there and got it all set up. We had a mobile ground command center that is that guy right there. As you can see, all the same kind of screens that we have in the big one. And then, yeah, we flew it around, and it does all kinds of fun little things. I think they do like the hat tip here, where it kind of bows to the crowd. Yeah, it was a really great example of kind of the future of aviation, because a lot of the aircraft that are there are kind of legacy and maybe even like really legacy, like World War I and World War II aircraft. There's also modern day fighter jets and stuff, but because you can kind of see some of the neat features that this aircraft can do. So it's just sitting there hovering in space, right? And then it can also just transition, which we did a couple of different transitions. And then last fall, we did something else kind of crazy with FAA's permission. We were the first autonomous eVTOL to fly in Los Angeles. So through our various partnerships, Long Beach is one of our partners that we're looking to launch operations from into the greater LA basin. And so in our collaboration with the airport, we took an airplane out there and did a kind of a friends and family day. About 15,000 people, or so 10 to 15,000 people came out, saw the aircraft, got to sit in it, all that kind of fun stuff. And then we did actual flight operations at Long Beach Airport, which is an international airport. So we believe it's the first time anyone's done a large air taxi autonomously at a commercial airport. So a lot of good stuff. And yeah, there it is. It's flying down the runway at Long Beach. It's fun because right after we had to wait for a 737 to land, and then the wait vortices had to subside, and then we took off and flew, and then right behind us after we landed, another 737 landed. So, and then yeah, these are just some of the public engagement things that we do, taking the plane out, talking about the future, all the fun stuff. I don't think I'm in this video, which is probably good for y'all. So, yeah, this is the Gen 5 look like inside. We have a lot of different ways that we kind of convey what this experience is like. That's a fun, it's like a cubby. You get in there and you see what it's like to be a passenger. So, yeah, and then that's the lineup of weight, the 737 to take off or to land there. And then this is just a fun thing. We were flying there in
electric. Operations 2410-4, completely electric. Interesting, cool. Yeah, you're looking at the beginning of the future here. It's coming fast.
So yeah, that's it. Thank you. So happy to answer any questions. I think I have 20 minutes or so. Thank you.
All right, any opening questions? Anybody in here?
I'll answer every single thing.
Yeah.
Beginning, you said, I guess he's your CEO's son, he looks fairly young. Eventually when that son does grow up and he's part of that like target demographic, you're like who is that? Like what's their lifestyle? What's their like price range for something like this? Like who you guys like intending to sell this to? Because the government stuff is super interesting, but in terms of like the individual people,
Yeah.
who's that look like?
Really good question.
And she's saying I'm too old.
Her words. So it's a really good question. So when we look at kind of early adopters, it'll probably, so let's see. Two of our friends in the industry will be entering into service next year. So a lot of people talk about, oh, well, where's eVTOL? Is it 10 years, 20 years out? No, that's actually going to start next year. For us, we always say end of the decade as to when we'll be ready. And it's because we believe it's a partnership with the FAA to make sure that this autonomous system is safely certified. So that all being said, assuming these actual operations start next year with some of our friends in the industry, you'll be able to ride one next year. And so you are the beginning of that kind of pipeline of customers. And we believe that as as younger folks come on to that pipeline, the bell curve of the life of this aircraft will probably be some of those. The baby. He wishes he was the CEO. He's our head mechanic. But yes, the baby will probably be one of the biggest users of our aircraft. We're finding that more and more people do not want to have a driver's license. More and more people do not want to own a car. They just want to be able to sit in a car, go somewhere, get off, and be done with it. And so that demographic is really becoming more and more attractive for us because those will be the folks that will be riding in the car. And we think that that's a trend that's going to continue. We don't think there's going to be a sudden interest and everyone starts wanting to own a car again and have a driver's license and all these things. So, but it's a really good question. On price point, it's about, right now we're targeting $10 a passenger mile because after that, you actually, it probably makes more sense for you to just you take an Uber Black and you could just sit there and have a good time in an SUV. That would be probably the upper end of it. Most of us are targeting $2 to $3 per passenger mile. So just use round numbers. You want to go 10 miles, $20 to $30. On a tough day, surge pricing, $100. You probably wouldn't go 10, you'd probably go 20. So now you get into like $200 on the high end. But bless you, if there are folks who really value their time, i.e. business travelers, for example, they may really want to pay that $200, especially because the business is paying nothing, that they may want to pay that $200 to get there and save themselves upwards of 30 minutes, an hour, 2 hours, depending on like at LA traffic. So, so those are kind of the areas we're looking.
Thank you.
Yeah, good question.
From a engineering question.
Yeah, go ahead.
I have one.
You go.
Student.
It was a question, like how big is your team and how much of the team is working on the battery side versus maybe the autonomy side, software side?
Yeah, so of the 800, I would say about, man, I wish my team was bigger. I think there's about 500 or so. Oh no, it's actually probably closer to like 650 directly engaged on the engineering side of things. And then within that, I think the battery team and the autonomy team, the hard part is I'm trying to like do the org chart in my head and they're all kind of matrix. So the better part of, 50 to 100 on those. So trying to increase those numbers always, because in the end, the key differentiator for us is around the electric and the autonomy. So, yeah.
All right, we're against the wall.
Yeah, so you talked about FAA regulations, stuff like that. Was there any part of the aircraft that like needed a new sector of regulations to address like certain problems? And also, kind of a second question is, how does the aircraft communicate with other aircraft in the sky, and like how do you navigate that, especially in terms of like collision avoidance and stuff like that?
Yeah, both really good.
Can you just speak generally about how regulations need to be, new ones or changed relative to drones or helicopters and these kinds?
Yeah, no, really good question. So the other half of my life is policy and regulatory. So the short answer is we're trying to leverage as much existing infrastructure, and I'll just put that in air quotes, as possible. And that could be physical infrastructure, charging infrastructure, regulatory infrastructure. So we're trying to take advantage of, okay, it says that to fly a small aircraft, you have to have, the aircraft must be certified to do the following things, to include the pilot will do X, Y, and Z. So we hone in on that specific, those lines within the regulations. We say, okay, what if it wasn't a pilot? What if it was a system? How do you feel about that, FAA? So then we can dig deeper, and the FAA says, well, okay, but a pilot we expect to be able to do X, Y, and Z. And we say, okay, well, here's where the system will do it in combination with the human advisor or supervisor on the ground. Is this good enough? And they say, well, what if you do this, that, and the other thing? So we start to negotiate, basically. So the idea is to reduce the barrier to entry for our commercial service by being able to tap into existing regulations and whatnot. Now, some of them, yeah, there will be some things that we will need a waiver or an exemption for, because the existing rule set is based on human pilots and human crew and these types of things. That being said, the FAA is absolutely leaning into it, which is great. They're seeing a lot of opportunity because they're seeing more and more highly automated systems in every form of aircraft, general aviation, business aviation, commercial aviation. So they know this is the future. And so there are many ways they're using our aircraft as a pathfinder. Now, doesn't mean it's easy. It's not going to be quick, but we believe that they are a good partner to be able to drive this safely forward. So that's on that side. So and to be clear, we kind of Wisk, we steer away from the drone regulations because that's a completely different risk category. If you don't, someone gets a burrito dropped on their head, for example, that's a different thing versus a 1,000-pound aircraft flying out the sky with people on board or cargo. So we kind of focus on the existing piloted aviation stuff versus the drone. The drone folks have done a great job though. They're making a lot of progress in that space too. I could do a whole other talk on that. Then on detect and avoid and communication. So today, the modern day National Aerospace System has a lot of communication that happens between aircraft, air to the ground to space, all that kind of stuff. So we, again, kind of, how do we tap into that without having to rewrite a book? So we have all the capabilities that you would see again in a modern day aviation, modern day aircraft. So transponders that kind of tell where we are, but then also we have the ability to receive other folks transponding signals. We have the ability to receive ADS-B and ACAS, ADS-B information from the FAA. We can actually have our own detection algorithms that we can deploy if for some reason, for example, there's someone in LA who routinely likes to fly a jetpack in and around the LAX arrival corridor for some reason. And so you can actually see this online. Pilots will report yeah, there's a guy up here in a jetpack, and they're having to avoid that person. So how do we make sure that our system is able to address threats like that? So it's a lot. The good thing is that the FAA especially has thought a lot about how to leverage existing information technology capabilities to have that at the disposal of everyone who wants to take advantage of it. So we just need to make sure the engineering system is able to ingest that and then also put it back out there for safe operation in that. So it's a good question.
Yeah. On your battery chemistry and technology selection, was that mostly driven by what you could get certified or what gave the highest performance? And if it was driven by the certification, you could have gone with something else. What would you have preferred to do?
Yeah, this is always a fun conversation between the R&D team and the cert team. And then in between is engineering, right? And so on the R&D side, they're like, look at all these amazing capabilities that are out there, especially automotive really pushing the envelope, high-powered, hand tools, drills and whatnot, also pushing the envelope, Formula E pushing the envelope. So some amazing technologies out there, especially as it relates to not just kind of anode cathode work, but chemistry itself inside. One of my favorite ones is there's a great example of a lithium ion battery. Someone takes a drill, it's in a firebox, takes a drill and drives a drill through it. Lithium ion catches on fire, thermal runaway, the whole thing's a mess. Then they've got a graphite based battery, drill a hole in it, just graphite shavings come out, no fire. Can't certify that battery yet. So there's the one end of the spectrum is how do you take advantage of these cool R&D technologies? And then how do the folks who do certification then have that part of the conversation of, yeah, but we're trying to figure out how to move this forward as quickly as possible, as safely as possible. So how do we use the technology that the FAA or other regulators know about, or that there's an existing standard for, or maybe there's a standard that we need to just tweak a little bit and they will pull that one forward. So it's a big conversation. And of course, engineering sits there and says, well, that design volume, that's not going to fit in this thing. We've already got the outer mold line figured out. So you need to find something else that's going to fit in there. For batteries these days now, it's either a pouch cell like you have in these little computers, or a prismatic cell or a cylindrical cell. Cylindrical is the one you always see, you put in your remote control on your TV and stuff like that. Those are the three main forms. So that in and of itself, that volumetric conversation about what's the right pack volume that you can actually get into the back of the fuselage, it's a huge deal. There's the chemistry side, just the physics of how do you fit all these things in here. There's a couple thousand cells in our aircraft. It's almost a metric ton of lithium ion, which is a whole other thing. When you think from a certification perspective, I can't even take my laptop and put it underneath the airplane in my checked baggage. I get frisked if you have an electric toothbrush, but we have a metric ton almost of lithium ion in the back of this airplane. So what do the firewalls need to look like? What do the thermal runaways mitigations need to look like? How do you vent off board while still landing the aircraft quickly? All that kind of stuff is all part of the certification opportunity.
Oh, okay. So the question gets a little bit into design. You have based on your Gen 6, picture, was it?
12.
12 rotors,
Yes.
right? So how many do you really need to take off? I guess it depends on the load, but for your targeted load, it's talking about safety and redundancy, is there kind of twice as many rotors or something like this?
Yeah, it's a really good question. And I actually didn't talk much about so our capability, this aircraft, it's basically those front ones are transitional. So they're obviously in a vertical configuration now. So the aircraft takes off and then those will transition to horizontal flight. The back ones will lock into place to reduce drag. And then, the process reverses itself for landing. So we believe that the 12 motor configuration, if you look at our friends in the industry, everyone pretty much has a different number of motors that they think is the right number. Again, that depends on your aircraft design, your use case, your business model, all that kind of stuff. So for us, we have designed that to be able to, that is the kind of the minimum and the maximum, so to speak. That's the kind of the optimization curve. We think 12 is the right number. Each one has 5 blades. We think that's the right number based on our motor sizing, which is based on our use case, based on our business model. So, and also, again, trying to drive to those higher levels of safety. What are the FAA gets to choose which ones they want to fail. So at any moment they say, okay, in simulated space, let's go ahead and fail 1, 3, and 5. What happens to the airplane? What do you experience any sort of adverse yaw? What is the pitch moment? What is the roll moment? What happens when all that happens? What's the passenger experiencing inside? What are they seeing on their little screen? Like, what are all the things that need to happen in that moment where contingencies are needing to be exercised? So these motors are sized to be able to lose a number of those, like I said, and still make a safe landing, which is, it's honestly, it's an engineering feat. So it's exciting. And even so, when you do see one of these Gen 6 aircraft, you'll notice that each of those motor heads is actually, is there a pointer on this thing?
It works. It'll.
Okay. So each of these motor heads is actually just slightly angled. So this one is the pitch, the plane of these blades is actually just below the plane of this motor. Plane of this set of the disc of this motor is actually just below the plane of this one. So that if at any moment one of these blades comes out, it doesn't conduct fratricide against the other motors. So that's another example of like just little tiny things. When you see the plane, you'll be like, most folks probably would not even notice that these were just slightly off by about 3 to 5 degrees. But that's an example of one way that we've thought about it. Also, when it's in the vertical setting, the plane of all of the motors in the front is in front of the front feet of the passengers. So that if you have a blade out condition when the aircraft is in the horizontal flight, the blade could potentially, and it also retention stuff and whatnot. But in a worst case scenario, it passes in front of the passenger. So again, little tiny details you have to think about for pretty much every contingency of flight. So
I've thought about that when I get on a propeller plane.
yes, and you can read about blade out conditions in jet engines and propeller planes. It's always exciting to see how that works.
You mentioned that design is sized to fit on, I don't know, helipad or a standard helipad size. And then you also mentioned partnering with lots of airports. So what's kind of the vision of the business model where you can take off and land? Like in places like Texas, you can kind of see that this is good because it's not easy to get from airports to downtown. So flying to the top of a building downtown seems feasible. So is that the kind of thing you're envisioning, or how do you think about the numbers of places you potentially want to land? What are the difficulties and opportunities, if you will?
Yeah, so it's fun. We have a whole data science team that looks at like where is the best opportunity to generate revenue and provide the service and that type of stuff. And so you can imagine it's big cities. I like to say it's big cities you can see from space at night. That's generally where our airplane will do the best. So it's LA, it's Seattle, it's Houston, it's Austin, it's Dallas, it's Miami, it's New York, it's all those places that you can kind of imagine where there's kind of 3 ingredients: large urban sprawl, traffic, and disposable income. The thing that actually slows down our entry into service, our desire to go to a market, is a reliable transportation system. So you can imagine that if someone has the option to take a train underground, for example, and they could do that for $5, why would they actually get on this thing? So this is actually just it's an option for folks who want to use it. In no way are we trying to force people to, this is the only method of transportation in your city. You should shut down all roads and ban all cars. This is just an option for a city to decide. But, so we have our data science team that looks at all these cities and says like, look, you could land, if you could land anywhere in this city, look at, these are all the people you could provide services to. And then we say, okay, yeah, but let's put on like the reality hat and say, we're only, if we want to wait for new locations to be built to land at, that's going to take another 10 years. And we'd like to get into business sooner than that. So let's constrain our assessment as to where's the existing aviation infrastructure, where are those helipads, heliports, airports that we can actually land at today. And then the data science guys go, oh, okay, well, that's there, and there. And so they're like, okay, you could go there, but look at all this future opportunity. And so that's where we actually, so we partner with the airports and the helipads and heliports where we need to. But we're also partnering with there's a whole ancillary industry that's bolted on to this one, which is the vertiport building industry, where these future vertiports, which are designed specifically for vertical takeoff and landing aircraft like these, they have the charging infrastructure, they have little lobby and stuff, but they're really designed to move and create a new set of infrastructure maybe in your town, maybe in your neighborhood, like on your cul-de-sac, like stuff like that. So that's where the next wave of this opportunity as it relates to aviation mobility, that's where it really kicks in. Because now you could walk to the place where you pick up the aircraft. You don't have to take another form of mobility. And so it's a whole other session with vertiports, because there's a couple of companies out there that are building vertiports. Actually, there's one based here in Texas, Ferrovial. They are the subsidiary of a major airport manufacturer. Yes, there are airport manufacturers. And so they're building vertiports. Ferrovial is building vertiports across the US to be able to give more people more access to these landing aircraft versus just going to an airport. So that industry will take a little bit of time. It's going to kind of follow. So as these aircraft get certified, then you'll see more and more vertiports being built. But there's a few being built. There's actually one up north in Dallas. There's a few being built outside of Miami. And there's others being built as we speak. So that will be a huge unlock for this industry.
All right, one question.
Just on business model, are y'all planning to be like owner operator or OEM?
Yeah, good question. We are planning on being the OEM and the operator. So in certification speak, we are a Part 121 production facility, and then we will be a Part 135 on-demand air carrier. For us, it makes more sense not to sell these aircraft because there's a lot to these aircraft. And so we just feel like it's better to partner with like an airline or a rideshare company or a cruise line or a hotel and just be their partner. Then that way they can just say, hey, here's a couple customers that want to go ride on the plane. We say, great, thanks so much. They ride on our plane. And then that's kind of how the relationship works.
Right, okay, that makes sense. All right, so let's thank Dan Dalton, Vice President of Global Partnerships at Wisk Aero. Thank you.